Hey everyone, this is a recording to walk through how to use Jamovi to perform regression analyses. To start, I brought in the Office Parks dataset that's on my website. So you can see when I brought it in, first thing, we don't need this first one, it's just a count of the rows. I'm going to delete that real quick. But you'll notice every name has a Venn diagram next to it. That means right now, Jamovi thinks that all these variables are categorical. Problem with that is we want to do linear regression, and many of these things are actually continuous. To start, I'm going to make productivity continuous. I'm going to come over to income, make that continuous. Scroll over to depression, make that continuous. And awkwardness continuous. That'll be enough for today's short recording. Now, each of those that I made continuous have the little scale next to them. That means that Jamovi understands what it's doing. Now we can click on regression, click on linear regression. This is going to pop up this window. I'm going to move it over so we can see a little bit better. As a reminder, the dependent variable is the outcome. It's the thing we want to predict. Covariates are Jamovi's term for continuous predictors, the things that are trying to explain the outcome that are continuous. You can see both of these, they are supposed to have that ruler next to them, they're continuous. And then factors are the ones with the Venn diagram. What we're going to try to predict is income. And to start, we're only going to bring over productivity at time 1. This is going to give us what's called a simple regression. It's simple because it just has one predictor. We're going to skip over model builder. We don't need to do anything in there. We don't need anything in reference levels. We are going to click on assumption checks. In linear regression, there's quite a bit that we can check. We don't need collinearity statistics. That only is for multiple regression. But we can check a QQ plot of the residuals and other residual plots. The model fit is going to give us some options of adding a few things for the model fit. For right now, R and R squared is what we need for the class. We're going to leave those the same. The model coefficients, often we're also going to want the ANOVA test. And it can be really good to get a standardized estimate. So we're going to include both of those, and we'll get a confidence interval for the standardized coefficient. We'll talk about what that means in a moment. And then this is actually going to give us a plot that we'll show at the bottom in a moment. Let's walk through what each of these pieces mean. When we added a few things, the model fit we already had before. To understand what this means, R squared is telling us a proportion of the variability in our outcome, which is income. If we go back up here, the dependent variable is income. That means productivity, it's our only variable. On its own, it explains about 33% of the variability in income. That's quite a bit. It's a large effect. The omnibus ANOVA test, you'll recognize from the ANOVA part of the class. This is just telling us that productivity significantly predicts the outcome. Right now, this doesn't tell us really anything more beyond what we're going to get in the coefficients. But it's good practice to have this, and there's going to be cases where it gives us really useful information, especially with categorical variables. Now, when we get down to the model coefficients, I'll scoot this over more so we can see the whole thing. This is where the information can be very rich for us. Productivity here is the line we're going to focus on. If you remember in the lecture, the intercept is just telling us what the average of your outcome is, in this case income, when all your predictors are 0. That means here that our average income would be about 24 grand for someone that has 0 productivity, who's doing nothing. In our data set, no one has 0 productivity, so this is not a super useful number, the intercept. So we're going to ignore that here. For us, productivity is going to tell us everything we need. First, the estimate tells us if we have a positive or negative relationship between productivity and income. In this case, we have a significant, if we come over to p-value, positive relationship between income and productivity at time 1. This unit tells us for every 1 unit increase in productivity, there is a 7.5 unit increase in income. In other words, if we increase our productivity by 1 unit, we would expect our income to go up by about $7,500. Over here, we also get our standardized estimate. This, in essence, is telling us our correlation. When it's just a simple regression model, this is equal to a correlation. So our correlation is 0.57. And this gives us a confidence interval of our correlation. Most of our interpretation is going to happen right here. However, in order for us to be able to say that our model means anything, we need to look at our assumptions. First, we're going to look at the residuals. This is going to check for normality. If the points are roughly along the line, then our normality is satisfied. In this case, it is. The points are roughly along the line. I would say this is pretty good. We don't have a problem with normality. And then the residual plots can also tell us if we have issues with linearity. Here, we're getting the model predicted values and the residuals. What this helps us understand is that we have a little bit of a curve happening here. That means that when the model predicts something really low, the residuals tend to be lower. And then in the middle, the residuals tend to be bigger, and then at the end, it tends to be smaller. Often when you're starting to see a pattern like this, you're starting to think, well, maybe the relationship between these two might not be perfectly linear. It also shows us income in the residuals and productivity in the residuals. Again, with productivity, we see this kind of curve. We don't talk about these a ton in this class. However, when we look at the residual plots, what we want to see is kind of a cloud of points. We don't want to see any patterns where maybe it starts low, goes higher, and starts lower, or any fanning out of the residuals where there's not much movement on this side and then it fans out and has a lot on this side. Those are the patterns we're generally looking for. This last part is the plot showing us the relationship between productivity and income. The shaded area, we can come down here and it'll tell us that the shaded is a confidence interval of 95%. Now, so we've done a simple regression at this point. Now we can add to it. Let's say we think that productivity is going to predict income, but we wonder if it's also income's affected by depression and awkwardness. So let's put both of those in there, and let's go back to the top where we have our results. Here we have our R squared. That's telling us productivity, depression, and awkwardness all together explain about 60% of the variability in our outcome. We come down to the omnibus ANOVA test. This is telling us that productivity significantly predicts the outcome, depression does not, and awkwardness does. If we come down here to the model coefficients, this will tell us the direction of the relationship and how big it is. For productivity, now that we're controlling for depression and awkwardness, for a 1 unit increase in productivity, we would expect almost a $5,000 increase in our income. In this case, a $4,950 increase in income. Depression, on the other hand, as it increases, we'd expect basically a $766 decrease in income. That is, more depressed people tend to earn a little bit less. But note that that's not a significant relationship. In other words, when we're interpreting this, we would say depression does not significantly predict income. And then the last one, awkwardness. It is a significant predictor of income. And what this one's saying is for a 1 unit increase in awkwardness, there is a negative 15 grand-ish decrease in income. So as you get more awkward, your income tends to go down. Because each of these are in the units of these variables, so this is for a 1 unit increase in productivity or a 1 unit increase in awkwardness, these things, this is what we predict to change in the income. We can use our standardized estimates to understand how strongly these are related to the income. This says productivity, this is approximating a partial correlation, which means a correlation controlling for the other variables. Here, productivity has a relationship of 0.36, depression negative 1.17, and then awkwardness negative 0.5. In other words, awkwardness is the strongest predictor of the outcome. Next is productivity, and last is depression. These values tell us if we change awkwardness or productivity, how much the income is going to change on average. This is telling us the strength of the relationship. Both of them are really important to look at when you have a multiple regression. Again, we can check our assumptions, and again, the assumptions are looking pretty good. The points are right along the line. This one looks better. It's more random, just kind of a random cloud. So we don't have the problem that we were having with just a simple regression. We come down to the bottom, and we can see the relationship between productivity and income when we're controlling for the other two variables. We can come down here and add these. We can add depression and add awkwardness. And that will create plots for each of those three. Okay, at this point, this may be a good model to go with. We could interpret it and move on. So we'll close this. But maybe we also wonder, well, I wonder if productivity interacts with another variable, maybe with whether or not they're married. That's totally not based on theory or research. It's just totally for an example. So let's start a new regression analysis. So I just went up to regression, clicked linear regression, and this popped up. Again, we want income as our dependent variable. Let's bring depression and awkwardness over. We still want to control for those. But now let me find married. I'm going to bring that over as a factor. As a reminder, why we're treating that as a factor is because it is categorical. We bring married over, and now this is what we have. We can come down and request a few things. We want the ANOVA, we want the standardized. We'll come back to the estimated marginal means in a moment. Here we have all of our output again. So far what we have is everything we had in our previous model, but now we have married. And it doesn't significantly predict the outcome. And it doesn't really help our R-squared. Our R-squared was roughly that to begin with. So married on its own isn't really helping our model at all. But our question is more, does it interact with productivity? So now this is when we actually use Model Builder. What we're going to do is we're going to add, so I'm going to select prod1 and select married. And I'm going to use the command key on a Mac or a control key on Windows. And I'm going to click here and add an interaction between these two. What this added was prod1 star and mar. This is the interaction. And you notice when I did this, it created this new line in this table. In this case, productivity and marital status does not interact. It's not a significant, there's no significant relationship there. And if we come down to our coefficients, we're going to see the same thing. There's not a significant relationship. However, in this case, let's say there is a significant relationship. The best way to really interpret what an interaction is meaning is to look at a figure. We're not going to talk about these values. We're going to come down to the estimated marginal means. What I want to add is both of these. So I'm going to select both of those again and bring them over. At the bottom here, we're now going to have a plot. What I recommend is if you have a continuous variable that it be the top one. So I'm going to scoot that up. It's going to change the plot. What we're going to see is productivity along the x-axis and income along the y. And this is not a significant relationship. However, this can still give us some ideas of what the relationship's starting to look like. So in this case, let's pretend this was a significant relationship. We have marital status 1, meaning they're married. That's this line. And marital status of 0 is not married, and that's this line. What this is telling us is that increase in productivity for those that are married has a bigger impact on income than if you're not married. If you're not married, then increasing productivity helps you a little bit. Still good for your income. But if you're married, it looks like it's really helpful for your income. It goes up even faster. If we come back up to here and we saw that this was significant here or here, they're going to tell you roughly the same information. Then we would interpret it using this plot. I hope this example has really helped you think through how to use Jamovi to perform regression analyses. I went through a simple regression, a multiple regression, and a multiple regression with an interaction. Reach out if you have questions about this. Give it a try with the Office Parks data set or with the poverty data set that I posted on my website as well, and see what results you come up with and post it on the discussion board.